Okay. Hello, everyone. Welcome to this afternoon's NITheCS seminar. So I'm substitute for the director, Francesco Percioni this afternoon to introduce the speaker because he's in another meeting. So today we are very happy to have Professor Soebur Razzaque, who is a distinguished professor of physics at University of Johannesburg. And he also holds the directorship of the Center for Astroparticle Physics at UJ. And he has been appointed as a research professor at the George Washington University in the USA. And he mainly researched on the astrophysics of the extreme sources in the universe, such as a gamma ray burst, and also active galactic nuclei, AGN. In particular, to understand the mechanism for emission of the high energy cosmic rays, gamma rays, and neutrinos. He also researches on the fundamental property of the of these particles and their interplay with the astronomical phenomena. He is also the co-I of the NITheCS research program, The New Insight into the Astrophysics and Cosmology with Theoretical Models Confronting Observation Data. I believe I'm also one of the co-I of the program. So, okay, the floor is to you, Professor Razzaque. Yeah.
I think I have my mic. Yeah. All right. Yeah. Thank you, Inze, for this introduction. Thank you, Francesco, who is not here. But also thank you, NITheCS, for having me here and giving me this opportunity to talk about my research. So as I said, I'll talk about gamma ray burst, and these are the most powerful explosions in the universe. And you may have heard about gamma ray burst in popular cultures, like the gamma ray bursts are the things that kill the dinosaurs. Okay, whether it actually happened or not, that's still inconclusive. But this is an active area of research to find the probability of having a gamma ray burst in close enough vicinity to the Earth so that they could actually kill the dinosaur. But the story of gamma ray burst began long after, if there was any dinosaur killing, any gamma ray burst killing the dinosaur. But it started with the nuclear explosion. That's another ominous threat to the civilization. So back in the 1960s, the nuclear test was happening on the Earth and also in the atmosphere. And there was a treaty between the US and the Russia, Soviet Union at the time, to ban these tests, especially in the atmosphere. And to monitor this ban, whether some other party is really doing the test or not, on the US side, they launched these satellites called Vela. It's a group of satellites, one shown here is a sketch. And these satellites that used to monitor the Earth for any sudden burst of gamma rays coming from these nuclear explosions. So in the nuclear explosions, it would be producing gamma rays, and these gamma rays would be escaping to the space, and then satellites looking down on the Earth could detect these gamma rays and enforce this ban on testing nuclear weapons. And by accident, it actually detected the gamma rays burst coming from outer space. So not from the sun, from the Earth, but I mean, they of course detected gamma rays, or could have detected gamma rays coming from the Earth from these nuclear explosions. But the gamma ray burst was accidentally detected by this satellite, and this burst of gamma rays came from outer space. Now, what is a gamma ray burst? So simply a gamma ray burst is a burst of gamma rays, as I said, gamma rays within certain energy range, usually tens of kilo electron volt to mega electron volt. And these are detected from satellites. So after the 1960s and the early 70s, the first gamma ray detecting satellites were launched in the early 1980s. This one is the more recent one. It's in orbit since 2008. It's called Fermi Gamma Ray Space Telescope by NASA. And a gamma ray burst is this sudden burst of gamma rays. What is shown here is the count of gamma rays per second, and this is the time and you see this huge spike in gamma rays. And at the time, you have this source, gamma ray source, suddenly appearing in the gamma ray sky. And this is an image of the universe in gamma rays. And this is the galactic plane. And this is where a burst is happening. And it outshines the entire universe emitting in gamma rays. So that's a gamma ray burst. Now, the characteristics of gamma ray burst is that it has this very sudden rise in the gamma ray count. And this is an image in gamma rays from this Fermi Gamma Ray Space Telescope. And it is a more recent gamma ray burst called GRB 130427A. So GRB is for gamma ray burst. And this telephone number is, the first two is for the year. So it is 2013, April 27, and A is the first burst of that day. So if there are more bursts, it will be A, B, C, D, and so on. And before the burst happened, this is the sky in gamma rays. And after the burst happened, this is the sky in gamma ray. You can clearly see this very bright spot in the sky in gamma rays. And typically, this kind of burst happens once or twice per day, but there are periods when there will be no burst for a few days, and then suddenly 4 bursts in a single day. So it's stochastic. And this is a map of thousands, about 3,000 gamma ray bursts collected over 10 years period happening in different parts of the sky. So this is a map of the sky in what is called the fluence, which is the collected energy in gamma ray with energy between 50 keV to 300 kilo electron volt. And this fluence is measured in ergs per centimeter square. So this is the energy collected by the satellites per centimeter square per unit area from this burst. And the characteristics of this burst is such that this fluence is from about, so this is flux. So flux is nothing but the fluence divided by the time. So the flux is 10 to the power minus 6 to 10 to the minus 4 erg per centimeter square per second. And as you can see, these bursts happening all over the sky. So that means they are isotropically distributed in the sky, which means they are coming from outside of our galaxy. So if they were coming from inside our galaxy, there would be a preferential direction where this burst would be coming from. But since they are distributed all over the sky more or less uniformly, that means they are coming from the universe, which is outside of our galaxy. And for cosmological distances, we use what is called the redshift. This is the dilation of frequency of light, or the wavelength of light. And redshift between 1 and 3, this peak of this distribution is between redshift 1 and 3, which means they are at very, very early time, or when the universe is very young. So if you take into account this distance for a burst and this fluence of the burst, then you can compute what would be the power of such an explosion. So the power of such an explosion would be about 10 to the power 52 erg per second. Now, as for comparison, our sun produces about 4 times 10 to the power 33 erg per second in energy. So this is more than 1 billion times more powerful than our sun. Okay. Of course, now we know that this energy is what we call the isotropic equivalent, meaning that if the gamma ray burst was emitting gamma rays in all direction uniformly, but now we know that the emission is probably beamed along some cone, some direction. So that means the actual energy release is about an order of magnitude smaller than this energy. But still, that is almost 1 billion times more power than our sun produces. Okay, there are 2 varieties of this burst. So one is called a short burst. So again, this is count of gamma rays per second, and this is the time. And the short burst appears like a very the tall spike over here, and not much. So it's suddenly the count rate goes up and then down. This is 1 second, 2 seconds, 3 seconds, 4 seconds. So in this case, the spike lasts for less than half a second. And there are long varieties or the long duration gamma ray burst, where you can see that there is this initial spike, and then there's a broader peak and a lot of fluctuations in the count of gamma rays over time. Okay? And if you take all the bursts and make a distribution of the duration, then clearly it shows a bimodal distribution of the duration. And the division between these two is about 2 seconds. So bursts shorter than 2 seconds, they're called the short bursts. And the bursts that are longer than 2 seconds are called the long bursts. And it turns out that this division, even though only based on observation, but actually refer to two different origin of gamma ray bursts. So this, as we'll see later, these gamma ray bursts originate from two different astrophysical phenomena. All right. Now, what happens after the burst? So you have this very spiky emission that lasts for a short period. But what happens after that? So it turns out that the story doesn't end there. So after this very explosive explosion, satellites have detected longer lasting emission in X-ray. So, and that is what is called an afterglow of a burst. So you have this initial explosion, and then you have a very long decaying emission phase that is called an afterglow of a burst. The first one was detected in '97 by a satellite called NITheCS, a Dutch-Italian satellite. And this is an afterglow in X-ray energies. And this is when you have the burst and the afterglow, and then afterglow fades away after some time. And this one is an image in the optical frequencies. So you have this burst, which happens over here, but with the optical telescopes, you can actually image the host galaxy, the galaxy where this burst came from, okay? So with the afterglow emission, then it's possible to find the host galaxy of this burst. And that tells a lot about the astrophysics of these sources. What kind of environments produce this kind of burst, or what is the redshift of this distance of this burst, and so on. And that is possible because of afterglow. And not only in X-ray and optical, the afterglow has been detected over all frequencies in all electromagnetic spectrum, from the gamma ray to the high energy N to the radio. And this is afterglow from a very, very powerful burst called GRB 130427A that I mentioned earlier. And this one shows that this emission, the flux and this time from the burst, so that the actual burst took place in this time range, and where you see a lot of fluctuations in the data. So that is in the 15 keV to 50 keV. But at higher energy, you don't see much fluctuation, but there is a gradual decline in emission in the flux. And this is at 100 GeV energy. This is at 100 giga electron volt energy. This one is at the X-ray energy, 0.2 to 10 keV. This is UV. This is optical, and over the top we have the radio emission from the burst at 5.5 gigahertz. So it is what we call the multi-wavelength emitter. So it emits from gamma ray at the high energy into the radio. And the characteristic thing to notice here is that all this emission, they gradually decline over time. So this is 100 days. Some of them are detected over 1,000 days after the burst. And this is the initial burst. This is the gamma ray burst where you have a lot of fluctuation, and this is afterglow of the burst. Yep. All right, now let us talk about the origin of this burst. So this long duration GRBs, they are connected with supernovae. Okay? You may know that the supernovae is the death of a star. So our sun will not die as a supernova because our sun is not massive enough. But the stars which are, say, 8 times, 10 times more massive than the sun, they die as a supernova, meaning that at the end of their life cycle, the core of those stars collapses and make explosion and make what is called a supernova. And it turns out the stars which are approximately 20 times more massive than the sun, they collapses to form a black hole at the center. Okay. And there are evidences, about 30 detection where astronomers have detected supernova associated with gamma ray burst, okay, with long duration gamma ray burst. The latest one is the very famous gamma ray burst GRB 221009A at very nearby, at a very close redshift 0.151. And these supernovae, they are typically what is called the type 1bc supernovae. So they come from very, very massive stars. Okay. And they're very bright. This peak magnitude can be 17, 18. And there are a number of these GRBs, as I mentioned, detected in connection with the supernova. So what happens is that the star here collapses, and then you have a shell of the star that expelled outwards because of this explosion, and that produces a supernova. But at the same time, a very energetic and collimated conical outflow of material take place. And that is what is called a jet. And this jet is what produces gamma ray burst. Okay. So in terms of the observational features, if you look at the light curve of the gamma ray burst, so as I mentioned, the afterglow of a gamma ray burst, you can measure in optical frequencies. So in this case, this is a gamma ray burst that took place in 2003. So we have data, optical data, observed this different wavelength, optical data from this burst, and you can fit a straight lines, and this is a log. This is a log plot, so which means the straight line is really a power law. And you can initially, this is the earlier time, initially you can see that this optical emission coming from the burst itself, the afterglow of the gamma ray burst. And this is later time, and you start seeing a bump. Okay? And this is more prominent over here. And this bump is due to the supernova. So the reason, even though the two events occur at the same time, so the jet is produced and the outer layer of the star, the envelope of the star, explodes around the same time, we see the supernova later on because it is much slower. Okay? So the jet expands almost at the speed of light, very relativistic, very, very close to the speed of light. But the supernova ejecta, that expands very slowly. Okay? So tens of thousands kilometers per hour speed. And and initially this envelope is very, very opaque, so that even light cannot escape, okay, from this envelope. But eventually when it expands, it becomes less and less dense and light can escape. And that's why it produces this kind of bump. And it is more detailed shown over here. Okay? So this kind of evidence tell us that the long duration gamma ray bursts, they are connected with supernova. They are due to death of very, very, very heavy stars in the universe. Okay? Now, what about the short duration gamma ray burst? Now, the short duration gamma ray burst, they come from the coalescence of binary stars. Binary compact stars, so something like a neutron star. Okay, so two neutron stars, they can form a binary. As you know, the most of the stars, about, well, not most, the half of the stars are in some kind of binary system. Okay? And if the two heavy stars are in a binary system, so both of the stars can explode and produce, say, supernova. And what remains after a supernova is what is called a neutron star. And these two neutron stars then would still be circling around each other and what is called the in spiral mode. And then they will come closer and closer due to emitting gravitational wave. Okay. And they come closer, and at some point they merge together and emits a lot of gravitational wave. Okay. So those gravitational waves have been detected by this detector called LIGO, a Large Interferometric Gravitational Observatory, LIGO and Virgo. So they detected this this kind of gravitational wave signal from merging of neutron stars. Okay. But by itself, it does not say about the gamma ray burst. But the interesting thing is the Fermi Gamma Ray Space Telescope that I mentioned earlier, and something like the Integral and other X-ray satellite, they detected a short gamma ray burst about 2 seconds after the LIGO detected gravitational wave from this event. Okay. So the order of the event is that you have this gravitational wave emitting, and it has this lot of emission in the final time when they merge together. And in the gamma ray, these are what is the gamma ray count, or the light curve. So this is the gamma ray count per second, and this is the time. And you see initially there's not much going on. There's a little bit up and down. These are fluctuations that come from the background. But the gravitational wave event happened here. The merging happened here. And this is the frequency of this gravitational wave. And after 2 seconds, you see this bump in gamma rays. Okay? You see it here, here in different frequencies. And that is a short gamma ray burst. Okay? Now, this event gave evidence that short gamma ray bursts, at least some of them, are produced by merging of neutron star. Now, in theory, it could be a neutron star colliding with a black hole, merging with a black hole that could also produce a gamma ray burst in theory. Two black holes would not produce a short gamma ray burst because there is no material to actually what is called the accreting or the converting material to energy. In that case, you need a neutron star. Now, in this regard, let me show you these movies for the two case. So this is a long duration gamma ray burst. So you have the massive star, it collapsed. The outer shell is still intact, and you have a black hole formed inside here. And there is some disk of material called an accretion disk. And the material falling into the black hole, they are ejected into this jet. And this jet propagates, okay? And the jet propagates, and then some bright part of the jet is where gamma rays, the initial prompt gamma rays are made. And then but jet continues plowing through the environment, and then it emits this bright part, means that they are producing this afterglow emission. Okay? So that is the scenario that the scientists have put together, the origin of gamma rays and the afterglow. But for the short gamma ray burst, this part still remains the same. So this burst and the afterglow still remains the same, but you replace this part with colliding, say, neutron star. And what happens here is that these two neutron stars, they spiral around each other, and they come closer and closer due to emitting gravitational wave, losing angular momentum. And then at some point, they merge and produce a lot of gravitational wave and also a short gamma ray burst. Okay. All right. Now, as I mentioned earlier, the gamma ray burst, they are jetted emission. Okay. So that means only a fraction of the whole solid angle, the emission happens. So that means if you are not along this cone, you would not see a gamma ray burst. Okay? And the jet emission, for example, in the case of binary collisions with a neutron star merging with a neutron star or a black hole, so this is the orbital plane, and the jet is launched along the direction perpendicular to this orbital plane. Okay, the two jet emission happens, one perpendicular in this direction and the other in the opposite direction. And the gravitational wave could be detected from this object, even though the jet may be pointing in different direction. The gravitational wave is omnidirectional, even though it's not isotropic. So some part is more stronger than other part. But the gravitational wave detector can still detect gravitational wave when the orientation of the object is at different angle in the sky, or the inclination angle is different. But to see a short gamma ray burst, you need to actually have the jet pointing in our direction. This is an image created by LIGO-Virgo collaboration. So there's two neutron star merging, and the jet is emitted along this cone. And the opening angle for this jet is about 30 degrees. Okay? That comes from observation of the gravitational wave and also the gamma ray burst, 170870. So if we are away from this opening angle, then we would not be seeing the burst. We'll still be detecting gravitational wave. Now, actually, this can be interesting to find how many of these gravitational waves will be actually producing gamma ray bursts that are pointing in our direction or not pointing in our direction. So that tells very important information about the rate of merger of this kind of event. Okay. Actually, one of my master students, Luyanda Maswi, did his MSc work on this. And he actually looked at 3 merger events detected by LIGO-Virgo in their O3 run. So that is from a few years ago. And these 3 events, they had at least one neutron star in the binary system. So these are the telephone number for those events: 1904-25, 1909-17, and 2001-15. The first one is a binary neutron star system. The only other binary neutron star event that LIGO detected other than GRB 1708-17. And these 2 are black hole neutron star system. Okay, so one black hole and one neutron star in the system. And he downloaded data from the LIGO-Virgo observatory and did a Bayesian analysis to fit what is called the waveform. So you have the predefined description of how the gravitational wave would be looking like, depending on the different characteristic of the binary system. And you use this fitting formula. So after running his code for about a few months on the CHPC, he then came up with this kind of plots in this corner plot. So he fitted like 11 parameters to the system with the goal of finding the inclination angle of the orbit. Okay? So if the inclination angle of the orbit is such that the jet is along our direction, or the inclination of the orbit is face on to us, that means if any gamma ray burst is produced, then you should be able to detect this burst. Okay? So, so he did all this analysis, find the inclination angle. So this one is for GW 1708-17 that LIGO-Virgo already has detected, and also the short GRB was detected from this burst. And these are the other 3 cases that he investigated. This one is just for the sanity check, and these 3 are for to see if the inclination angle of this would be in some orientation that is face on to us. And he found that in these three other cases, the inclination angle was such that the short gamma ray burst, even if it were produced, may not be actually pointing in our direction. Okay. And then one can calculate the rate of such detection for these 4 different events that LIGO detected. This black hole neutron star rate is comparable with the 0, but the neutron star rate is about 1 or 2 per year. Okay. And then one can also calculate what would be the probability of jointly detecting gravitational wave event and the short burst. And it turns out that we expect to detect a short gamma burst only in 1 out of 9 merger event for a neutron star merger or a black hole neutron star merger. So this work is will appear in monthly notices, Royal Astronomical Society soon. Okay. Now another question in gamma ray burst is what actually powers this jet? Okay. So in case of supernova, you have this explosion, okay, that expels the envelope of the star, and it's a once-off event, once-off kick given by the pressure. People think it is from the neutrinos that expels the envelope, and it expands over time. Now, in case of gamma ray burst, you actually need to have kind of an engine, okay? Kind of an engine that actually powers the jet for some time, whether it's a fraction of a second or whether tens of seconds, but you need to continuously supply energy, maybe on and off, but you still do need to do that. And that's a big challenge in this field to find out what actually powers this gamma ray burst. And one mechanism is called this Blandford-Znaik process, where you extract energy from a rotating curved black hole with a magnetized accretion disk. Okay? So this is kind of like similar to the Penrose process, but there are subtle differences. I'll not go into details of that, but it turns out that you can actually extract power from the black hole, a rotating black hole, through this mechanism. And the power is similar to what one needs to make this gamma ray burst. Okay? So remember that I mentioned about the 10 to the power 50 152 erg per second power, and this is about 10 to the 51, but it depends on all these parameters, right? It depends on the mass of the black hole. So if you say mass of the black hole is higher than the mass of the sun, then you get more power, or the magnetic field in the surrounding environment is very strong, then you get more power. Okay. All right. So let's move on. So far I have discussed about the GRBs, what they are, what are the different kinds, how they are produced. But the GRBs can also be used as probes, okay? Because they are very, very powerful. And if they happen at a very far away, at a high redshift, very far in the past, we can still detect them. Actually, the highest redshift of a gamma ray burst detected is about 9. Okay? And until recently, that was very, very far away. So I think right now the farthest galaxy detected is about redshift 10. Okay? So these bursts are very, very far away. So they can be used for cosmological application. Now, this is a previous work of my former PhD student, Feral Dirisa. So what we did, we tried to see if the gamma ray burst can be used as cosmological standard candle. So you know about the type 1A supernovae. So the type 1a supernovae, they are used as cosmological standard candle. So that means if astronomers can detect a type 1a supernovae and follow their light curve, then there are certain way that you can calculate the distance of the supernova. Okay? And that is because all these supernovae, they emit essentially the same energy. Okay? Now, in case of gamma ray burst, so if we can somehow standardize the emission from a burst, that by just observing a few parameters, we can tell what is the redshift of the burst, then it can be used as cosmological standard candle. And it can be it can be useful because the supernovae have been detected only up to redshift, say 1.4, maybe up to redshift 2 more recently. But the GRBs, as I mentioned, can be detected from very far away, even redshift larger than 8. And there are some interesting idea that it can also track the dark energy parameter, the dark energy density in the universe, even very far in the past. And this one shows what is called a Hubble diagram, where this type 1a supernovae, they are shown as these black points over here. And then these are gamma ray bursts. So as you can see, the gamma ray burst can extend to very high redshift, so where there is no supernova. Now, of course, to make the gamma ray burst standard candle, it does not come out automatically. So you have to find something, some features to make them standard candle. And in the literature, people usually use this kind of phenomenological correlation. So that means they are based on observation. One is called the Amati relation, which relates the total isotropic energy. So that means if the burst was isotropic, emitting gamma rays in all directions, so the total energy with the peak of the spectrum. Okay, so the spectrum means that gamma rays are emitted over many energy intervals or frequencies, but it peaks. The most of the energy comes in certain frequency, and that is the peak of the spectrum. And this is a relationship between the total energy and the peak of the spectrum. So if this relationship is valid, by just measuring the peak of the spectrum and knowing what m is, we can calculate what is the total energy, isotropic energy released by the gamma ray burst. And since the total energy depends on the luminosity distance, how far the object is, because we don't measure the energy, we measure the fluence or the flux, as I showed in an earlier sky map. So that means if we know the fluence, okay, and this peak energy, we can calculate the isotropic energy by assuming some cosmology. Some cosmology means that we need to know the luminosity distance, and that luminosity distance depends on the cosmology. Okay. So that's one way of doing it. Another way is what is called a Toku relation. Again, that's quite old. So, but in this case, it relates the isotropic power or the luminosity with the peak energy. So what Ferrell did is using this Amati relation. So he used a sample of 119 gamma ray bursts with known redshift. Okay, with known redshift, and he then was able to use this relation to constrain the cosmological parameters. In this case, this omega lambda is the dark energy density, or the cosmological constant, and this is the Hubble constant. And this is the best fit, which comes out to be about 73, 74 with some large error. And the problem is the sample is still very small, so it's only 119 GRBs at the time with known redshift. But he can combine this with the type 1a supernovae, known at the time, about 580 of those supernovae, and combine the supernovae and GRB and make better constraint on the cosmological parameters. Okay, and it turns out this cosmological fit gives a Hubble constant close to 70. And if you are in the field, know about this so-called Hubble tension, that how the universe is expanding. There's a debate going on. So there's one set of measurement from the supernovae and the Cepheid variables, and then another set of measurement from cosmic microwave background, and they differ by more than 3 sigma. And that's what is called a Hubble tension. And interestingly, it turns out that this value is kind of in between these two extremes. But as I mentioned, this number is not large enough. So 119 GRB, that's very small compared to, say, 580 supernovae sample. So then it follows by another work by my current PhD student, Tamador Aldoma. So what we decided or thought is that we can increase the number of GRBs by estimating their redshift. Now, there are only 119 GRBs. Maybe today it is 130 GRBs with measured redshift. The redshift is measured with optical telescope by looking at the spectrum, and then they measure the redshift. But we thought that we could make estimate of the redshift using machine learning technique. Okay? That we look at the observable feature of the GRBs, okay, in the catalog collected over, say, tens of years by the satellite, and then we can estimate their redshift. And in estimating their redshift, we don't need to rely on this phenomenological correlation. We can directly input features into the machine learning algorithm and get out the redshift. And there's a potential to get a large number of GRB with redshift. So currently there are close to 1,900 gamma ray bursts detected by this Fermi Gamma Ray Space Telescope, and a smaller number, 276, detected by this Russian satellite called Konus Wind. And today, only 226 of these GRBs with measured redshift. So, so this is kind of like the what is architecture of a machine learning program that Tamador used. So what is this called a stacking ensemble method. So you have the input parameters, that the feature of the gamma ray burst that solely comes from observation and fitting the observed data. No need to use a cosmology here. And these input parameters are based on things like the spectral features. So you feed the gamma ray spectrum, and you get the parameters from fitting the observed gamma ray spectrum, and also the duration of the burst. So you plug in there, you reprocess data, and in this stacking ensemble method, she used, say, 3 different deep neural network model. And the final model is what is a random forest. And then finally, you get a redshift called the pseudo redshift of the burst. Okay. And then you can increase your sample. So in this case, these are different machine learning model that are used to train on the data set with known redshift. So this is the training data set, the testing sample, and these are the estimated, the pseudo redshift and the true redshift. Okay? And these 3 sets are for different spectral models used to fit the gamma ray data. And then we have a bunch of models here. So all of these rows is a model, and we estimate that the R-square, the correlation parameter, and the mean absolute error to find what would be a good fit to the data. And it turns out this we have the two satellite data samples, the GBM and the Conus wind, and we also combine these two samples into one and fit the similar model. And it turns out that if we combine the Conus wind and the GBM data, then if we also combine the Compton fluence and flux, the technicalities, and don't need to pay much attention to this, but things like we get pretty good fit, okay? So in this case, for example, R squared is 0.86, closer it is to 1, the better, and the error is is about 40% error in this estimate. Now, but then once you have machine learning model, so you can, from the applying it and the train it on the true redshift data, you can then apply it to find the pseudo redshift, okay, on the sample. And we after estimating the pseudo redshift, we then find how close the pseudo redshift distribution is to the true redshift distribution of this GRB. So this is an example of a good fit where we use a two-sided KS test to find these two distributions are from the two distributions are drawn from the same sample or not. And this blue histogram is the true redshift distribution, and this green histogram is for one of the machine learning model. And this corresponds to this case where the p-value for the KS test is 0.83. Okay. And this is an example of a not so good distribution where this p-value for the KS test is about 0.15. So this is not much a good representation of the true redshift distribution. And then you can do more. You can do some more testing, and you can compute now your isotropic energy and the isotropic luminosity from the fluence and the flux. Calculate your luminosity distance, assuming some cosmological model parameters. We use the currently used best fit model parameters, and then you evaluate the errors on this on this fit, and get a likelihood estimate, and then you can actually make plot of this Amati and Yonoteku relation that I mentioned. Okay, so that there are 4 plots here for 2 different machine learning model and 2 different spectral model here. So this one is for one of the machine learning model which did not give much good fit. This one is for one of the machine learning model that gave good fit. That means the p-value was large for the KS test. And this is the Amati relation. The gray points are for the pseudo redshift data. There are about 1,700 of GRBs now. We can estimate the pseudo redshift. And these red points are the GRBs with the true redshift. And so this is the isotropic energy release, and this is the peak of the spectrum. And you can clearly see this correlation. And these 2 samples, the pseudo redshift sample and the true redshift sample, they are close to each other. This is for this Amati relation. This is for the Yonoteku relation, where we have the luminosity and the peak of the spectrum, energy spectrum. And again, the gray dash lines, gray dash points are for the pseudo redshift. Again, about 1,700 of those GRBs. And then these red points are for the true redshift. And again, this is another case where the fit was not so good. There's a bit scatter in these data sets over here compared to these data sets. So we found that it is possible with using the machine learning technique to estimate the redshift of the GRB sample. And those GRB samples can mimic the actual sample of the sample of GRB with the actually measured redshift. More recently, we are looking to use this pseudo redshift sample for cosmology purpose. It's a work in progress, so we are trying to use this pseudo redshift sample to constrain the cosmological parameter in the lambda CDM cosmology with a flat lambda CDM cosmology. That means omega lambda and omega matter, their sum is equal to 1. But it turns out that it's even with this pseudo redshift, it can be a bit challenging. So what we try to do is we first fix the Hubble parameter and then see if we can constrain the omega lambda. And it turns out that if we are in a high redshift universe, so very early on, redshift between 4 and 5, so in this case, there are only about 4 actual GRBs with measured redshift. But there are a large number of, say, 53 GRBs with the pseudo redshift that we estimated from machine learning. And then you can try to fit your model. So what we do is we fit those parameters of this phenomenological correlation model, in this case, this Tiku relation model, and the cosmological model parameter at the same time. And this corner plot show that this is this omega lambda, which now actually gives a value which is interesting, 0.726. And then these are the other parameters for this fit parameters for this phenomenological relation. So, so this is still a work in progress, and we see that there is actually a potential that if we can increase the number of GRBs with the known redshift, then it may be possible to actually constrain the cosmology at the very high redshift universe. So it's an indication. I mean, we are not claiming anything yet because it's still in progress. Okay, so with that, let me come close to the conclusions. So there are a number of questions that are outstanding in this field. Some of them I mentioned, that how this central engine, a black hole, or a very magnetized neutron star called a magnetar, they produce these GRBs, how they are formed, and they produce the GRB by extracting energy from the black hole or these magnetars. How these relativistic jets are made, so the plasma moves at very close to the speed of light in a small cone. Also, we want to know how often these gravitational wave events, like merging of two neutron star or a black hole or neutron star, produce a short GRB. And the last part I mentioned, whether the GRBs are cosmological standard candle or not. Okay? Because they are the long duration GRB originate from the supernovae. So the total energy budget is constrained in such a system, right? You have the mass of this object kind of like constrained within a few solar masses. And lastly, but I did not talk about it, that there have been recent detection of very, very energetic gamma rays from gamma ray burst. The tera electron-volt energy is the kind of energetics you produce in the Large Hadron Collider, okay? At CERN, particle collider, but we have detected this very energetic tera electron-volt gamma rays from gamma ray burst more recently, and we still don't know exactly what are the processes, particle physics processes producing these gamma rays. And lastly, as I started earlier at the beginning of my talk, whether such a gamma ray burst can happen in our galaxy or not. So there are estimates ranging from, say, one event per few 100 million years to no event in the history of the universe, or the 13 billion years. All right, so with that, let me conclude. But lastly, I wanted to introduce my group at the gamma ray burst group at the University of Johannesburg. So we have a visiting professor, Lily Yang from Sun Yat-sen University in China. Jagadish was my postdoc before, now is a staff astronomer in India. My current postdocs, former PhD student, and the current PhD student, and the master's student. And with that, let me thank you.
Hey, questions to the speaker? Yeah, there it is. So we'll just wait for the mic.
Good afternoon. Thank you for a very informing talk. Maybe as a very simple question, but from what might be the origin of the gamma ray burst, have we ever seen a source repeating? so repeating at all? I guess not. And then my second question is: do we have an idea of the magnetic fields involved with the objects in relation to these gamma ray bursts?
A very good question. So for the gamma ray burst, we have not definitely detected burst from the same direction in the sky repeating. However, there are some cases, very few, and still they're debatable, that we see the similar pattern in the emission, almost identical pattern in the emission, coming from slightly different position in the sky from a previous gamma ray burst. Now, one interpretation is that this is because of what is called a gravitational lensing effect. So the original burst came earlier, some years ago, and then because of the gravitational lensing, light bended and then took a longer path to come to us, but producing the same kind of feature in the emission. So that's one possibility. I mean, it's not, there is no very strong evidence for that. And you probably know there's some other astrophysical objects like a fast radio burst that is actually known to have some repeating objects. So where you have the repeated radio emission coming from some of these objects. But that's a different scenario. And in case of gamma ray burst, it is believed that these are cataclysmic events. So it's a once-off. So once this happens, there is no way of repeating it. There is nothing left to actually repeat such event. But for the first radio burst, I mean, there are models where it could repeat itself.
Okay, more questions?
So sorry, the magnetic field I did not respond. So, but in one of the equation in the Blandford-Znaick, because you saw that you need about 10 to the power 16 Gauss on the surface of the magnetar or the black hole. So that is extremely strong. So in the regular neutron star, the magnetic field is about 10 to the power 12 Gauss. But objects with more than 10 to the power 13 Gauss or 14 Gauss, they are called a magnetar, so highly magnetized neutron star.
Okay, Herbert?
Yeah, is it?
One.
Okay, thanks a lot. Okay, on that slide, you mentioned that the particle physics for the high energetic gamma rays is unknown. So then let me ask, what is the situation for less energetic photons? Is the particle physics known? And eventually, would we see other particles coming out from these bursts like neutrinos, or is that
right.
also open?
Yeah, that's a good question. So for the usual gamma ray, the emission during the burst and afterglow, where you produce, say, giga electron-volt particle, giga electron-volt gamma rays. So we more or less know the origin of those. So they are coming from the synchrotron radiation by electrons. So the electrons are accelerated in kind of shock wave when the plasma in the jet collides with each other, or the plasma plows into the interstellar medium and producing a shock wave. And the particles can be accelerated in this shock wave, but this shock wave also compresses the magnetic field in the surrounding environment, or generate magnetic field because of some turbulence in the plasma. And the electrons, the relativistic electrons, then can gyrate around this magnetic field and produce what is called the synchrotron radiation. Also, it is possible to have the Compton scattering, where the electron can also upscatter some of the photons, okay? Either from this pool of the synchrotron photons, or the photon from the star itself, or in the or in the surrounding environment like CMB, and then Compton scatter this photon and move it to the higher energy. So these are the two particle physics processes that are well known, and we believe that they are the reasons for emitting these gamma rays, and also this radio and other things, X-rays. But for this very energetic one, especially the tera electron volt gamma rays, it turns out that it may be possible that we have some other particle physics processes when a hadron, a proton or nuclei, they are also accelerated in the shock, and they interact either with the photons or with the gas, and then produce this the pions. And these pions, either neutral pion or charged pion, can decay. So the neutral pion can decay into gamma rays. The charged pion will be decaying and can produce neutrinos. So these are some of the scenarios people have considered. But no neutrinos have been detected from a gamma ray burst yet. So we would not know for sure whether this process is actually taking place or not.
So you say the high energy TeV photon actually coming from the rest mass energy of these hadrons, which might be accelerated and somehow being converted into pions. It's extraordinarily high, so it must come from some.
It may come from the pions. So the protons, yeah, they can accelerate and interact and produce these pions to make this very energetic gamma ray. It may still be possible that this electromagnetic interaction, like Compton scattering, may produce this. But with the Compton scattering, there is what is called a Klein-Nishina effect, where the cross-section actually decreases at very high energy. And that actually prohibits production of a lot of very energetic gamma rays. So the Compton scattering, the electromagnetic process, is still not ruled out. But there is a possibility that this protons or hadronic interaction take place.
Okay, do we have a question online? Yeah, just one question online, then we close.
Hi, it's Renee here. We've got two comments here. Stefan Lotz says, not a question, more of a comment. We observed the recent GRB 221009A in VLF observations in the ionosphere, similar intensity as a weak solar flare. I'm not sure how interesting this would be to the speaker. I'd like to contact them about this event, as I don't understand the causative mechanisms well. So I'll connect the two of you via email. And then Rodri Evans says, I was involved in work to look at the visible light afterglows of GRBs back in the late 1990s with Don Lamb when I was at the University of Chicago. I'm pleased to see how much the field has advanced since then. Thank you.
Thank you. Very interesting comments. And yes, for this GRB that took place 2 years ago in 2022, and that actually did disrupt the ionosphere on Earth. So you need about 0.1 Earth per centimeter square fluence the flux to actually disturb the ionosphere. So you will actually have some effect on your communication. But those are kind of like very rare events, maybe once in a few years. type of event, they will disturb the ionosphere. But that's an interesting aspect of this.
Okay, so it's 5 p.m. So I myself also have questions. I will ask him offline. So I have 7 questions on my list on my cell phone as I record. But that's all. I'll spend that in my dinner time. Let's thank our speaker again.